Welcome to Surviving Until Dawn. I'm Bart. Before I get started, I'd like to give you a glimpse of what we'll be discussing today. I'm going to define the problem and explain why you should develop your own custom signatures. I'm going to examine some tools that you can use that uses detection signatures. We're going to walk through actually using some of the tools, talk about how you can create your custom signatures. We're going to consider some things that you should consider to avoid false positives and false negatives. And finally, we're going to bundle it for remote deployment. So who am I? I've been using computers since the early 80s. My first computer was a Commodore VIC-20 with 3.5K of memory. I used to buy the Compute Gazette magazine at the local Kroger store, and I would type the basic programs in the back for days on end, in the hopes that they would finally run. In my professional life, I work for a financial institution, and as part of my job, I assist and advise over 400 other financial institutions. Many of these are small and medium-sized businesses that are below the security poverty line. They're not able to afford expensive devices that can help them secure. So I've devoted a lot of time and energy to creating ways that small businesses can help defend themselves. On a personal note, my wife and I are celebrating our 30th wedding anniversary this year. In honor of this occasion, we took our grown children on a trip to Europe this summer. It was really amazing. We went to Belgium, the Netherlands, and the Czech Republic. Prague was absolutely fantastic. We stayed in a hostel just a couple of miles outside of the city center, and nearby was a, believe it or not, Mexican restaurant in Prague. We would eat breakfast there every day, and while we were there, I saw something that I want to share with you. And that has to be the most interesting toilet in the world. This thing was really amazing. It had one of the tanks that goes up towards the ceiling with a pull chain. In the back of the seat was an infrared sensor that would detect when the toilet was no longer being used. Once it detected that it was empty, an arm would come out of the middle of the back and it would start washing and sanitizing the seat as the ring of the seat slowly rotated underneath it. Now you may be wondering, what does that have to do with malware? Well, it sort of describes the problem that we're facing with our traditional off-the-shelf software and their antivirus programs. You're relying on signatures that were created by somebody else that were looking at unique pieces of software that they have seen. It may not be what you're facing. And then they chose what to examine when they created their signatures. That's sort of like this toilet. If I were to describe a toilet, I would say that it was a porcelain fixture with a back that held a tank that was attached to the seat. There would be a chrome lever that you would push to flush it, and the seat would raise from front to back. That description would fall apart if you were to look at the toilet that you see on your screen. But you may be wondering, why is it a problem? After all, I have an antivirus program with the latest virus definitions. In my daily job, I see a lot of malware. And it's not uncommon for a phishing campaign to come out and the malware that's attached to be undetectable by all the antivirus programs that are in use on VirusTotal. It's usually about a week after a phishing campaign before the signatures are created, they're quality tested, and they're deployed and finally installed on the endpoints. But a lot can happen in that week. We need a way to survive until dawn when the new signatures come out and come to our rescue. Because a lot can happen in a week. If you're a small business, you could have your entire bank account emptied. You could have your credit card data stolen or your intellectual property exfiltrated. And in the case of something like CryptoLocker, you could allow people to encrypt all your data in 1 week to hold you ransom. So where do you begin? The first thing is to understand what is normal inside your network and form a baseline. What you see on your screen is a normal Microsoft Word document that's open in a hex editor. And you can see that there's huge sections of null bytes that are used as padding within the document. On this screen, you see a resume that was sent to HR, and where it should have null bytes, it has question marks. Something was odd. This particular document was scanned with an antivirus program and the most recent virus definitions, but nothing was found. But fortunately, one of the tools I'll be talking about a little bit later, Yara, detected something suspicious. It disclosed that this document had been XOR encoded with the value 3F. And so once I decoded the document, I could see an embedded executable inside it. If I deleted everything before the MZ header and saved it, I actually had uncovered the Zeus Game Over Trojan. This next example is something that is not strictly incident response. It's in case of certification and accreditation, which, if you think about it, they're opposite sides of the same coin. We often have to investigate some new software to make sure that it's not malicious. In the case that you see on your screen, I made a mistake when I created the Yara rule, and I want to share that mistake with you in the hopes that you don't make the same mistake. What happened is we had a new system that we put up in my environment, and it was put in an isolated network segment with default deny firewall rules. And then only the rules that were required in the vendor documentation were opened up. Oddly enough, it began beaconing to the internet. The traffic appeared to be NTP traffic to try to set the time. You may be thinking, well, what's so wrong with that? Well, see, this machine had a defined time source, and it should not be trying to beacon directly to the internet. So I contacted the vendor to inquire what was going on, and they didn't know anything about it, and they suggested the machine may have been compromised, and they suggested reloading it. Well, if you want to see a financial institution get really upset, suggest that a machine in an internal network segment has been compromised without being detected. The chase was on. So the first thing I did is I used my go-to tool, Yara. And as I mentioned, I made a mistake when I created the rule. If you look at the hex display in the back, you can see the IP address is separated by null bytes. That means that it was stored inside the file as Unicode. When I wrote the Yara rule that you see on the screen, I left out the wide clause. So it was looking for normal American ASCII, and it did not find that specific IP address. But I want to show you how much time and effort that Yara would have saved me had I written the rule correctly. So since the scan did not reveal anything, the first thing I had to do was start looking at the network traffic with TCP dump. That allowed me to baseline how often the machine was attempting to beacon out. Once I established a pattern, I got on the machine and I used a netstat command to identify the process that was trying to do the network connection. It turned out to be a service process. And so I immediately scanned the machine with Yara again, which was my second opportunity with the false or inaccurate rule, and it didn't find anything. So I was able to use the sysinternals list DLLs file to identify all the DLLs that were loaded, and I scanned those as well. It didn't find anything. So next I loaded the executable up into IDA Pro and began poking around, but I didn't see anything that looked suspicious. Nothing really stood out. So I started tracing the code in Ollie Debug, and I discovered that whenever the service process restarted, it would force it to connect out to the internet. I was on to something. So next I used the Rohatab API monitor, and I could monitor the service process when it began and start looking for any kind of network calls. I immediately found where it was trying to make the connection, and I could see the arguments to the function call were in Unicode. So I realized what had happened. I adjusted my Yara rule, did the scan, and I actually found the IP addresses embedded in some DLL files. I loaded the DLL files, which turned out to be .NET assemblies, into ILSpy, and I started looking at the logic. it turns out that the IP address was being called as part of the copy protection scheme. And so I don't know if the vendor did not know about it or didn't want to reveal it, but either way, that's a problem with secure systems. So where do you get started? The simplest tool to use for creating a signature is ClamAV. ClamAV was created by SourceFire, which was bought by Cisco last year, and I hope that Cisco maintains their support of open source software. There's a distribution of ClamAV from clamav.net, but the one that I use is from clamwin.com, and it allows you to do an on-demand scan instead of the automatically running full-time scanner at clamav.net. The simplest way to create a signature is to grab a hash of the file as a whole. And you can do that many ways by using something like MD5Sum or Python, which we'll be looking at a little bit later. If you want to grab a hash of the individual file sections, you can also do that and save it into an MDB file. Or you can actually go into byte patterns and save that into an NDB file. Yara is the next tool that we'll talk about. It was created by Victor Alvarez from VirusTotal, and it's got a very expressive language for creating signatures. It basically starts with the word rule followed by a rule name. After that is a pair of curly brackets. Inside the curly brackets you have two mandatory sections, the string section and the condition section. You can have an optional third section called the meta section to put comments or other type of information that can be used by other tools. The string section is where you put the items that you want to locate inside a file or inside of process memory. And you can look for literal strings by enclosing them inside double quotes. If you want to look for individual byte patterns, then you can put the hexadecimal byte codes within curly brackets. It supports regular expressions by enclosing the target within forward slashes. It supports wildcards either on the whole byte or on a half of a byte, which is called a nibble. It supports jumps, alterations, and it can ignore case, or as we saw earlier, it can consider standard American ANSI ASCII or Unicode. Now the condition section has a support for a wide array of relational operators. You can look for the presence of an individual item or the presence of something in combination with something else. You can count the occurrences that something happens, as well as look at the file or memory offset and even compare the size of the file. Yara was modified in August of this year to allow the creation of custom modules if you can program in C. And so you can add to the functionality that's built in natively. The next tool that we're going to discuss is Python and the PE file module that's available for Python. Python is a wonderful tool for doing security work. It has a lot of libraries built into the standard distribution. But there's sometimes that you need some other modules that have been created for Python. In this case, the PE file module. To import the PE file module within Python version 2, the older version, is fairly straightforward. You just download the module and then you use the setup script within it and it'll copy the files into the correct location. Now the newer 3.x version, you will have to make a modification to make it work correctly, and that's in the hex digest function. It's unable to handle Unicode, and so there is a bug that you need to make this change that you see on the screen. So let's talk about how you would actually scan things of interest on your system. Back years ago when Microsoft created the Windows NT operating system, they created a new file system called NTFS, and they wanted to add support for resource forks such as were in Macintosh computers, and so they created something called the alternate data stream. Alternate data streams are created by creating a file name that's got a colon in it. So if you look at the example on the top of the screen, I'm echoing the word Yara and I'm directing the output to a file called hidden text: hidden text. Alternate data streams are hidden from the operating system utilities, and so if I do the directory command, you can see that it appears to be an empty file. Malware authors discovered that the utilities built into the operating system wouldn't detect alternate data streams, and so they began abusing this functionality by hiding malware or even data that they were exfiltrating. Microsoft realized this was a problem, and so they added the /r switch. And so you can see that if I use the /r switch to the directory command, it reveals the presence of an alternate data stream. In this case, there's 7 bytes, which is the letters spelling out Yara, a carriage return line feed, as well as an end-to-file marker. So how do you scan an alternate data stream if it's not natively detected by the operating system? One way is to use the Windows port of the GNU utility cat. You can cat an alternate data stream and direct the output to a new file with a file name that you can scan. A lot of times malware will hide configuration information or even binary code within the registry. If you want to scan that, you can open it up into regedit, select the hive of interest, right-click, select export, and save that hive to a text file that you can scan. If you prefer the command line, you can use the reg command with the export option. ClamAV supports the ability to scan disk images as well as memory, well, so does Yara. You can actually scan the file system, or you can scan the process memory. It supports a -S option, which will show you the location of the match. Now what this number represents is a little bit confusing, and so to get a grasp of what that means, you need to have a little bit of an understanding of the Windows PE file format. You see, every Windows executable that's in the Windows PE file format follows a consistent pattern. It always begins with the capital letters MZ as the first 2 characters of the file. At position 60 through 64 is an integer that points to the location of the PE file header. The PE file header always begins with the capital letters PE followed by 2 null bytes. After the PE file header, you have the image optional header, and despite its name, it's not optional. After the image optional header, you have the section table that points to the locations of the individual file sections. So getting back to scanning a process with Yara and the -S switch, it will actually reveal an offset that is within one of the file sections. Unfortunately, it doesn't tell you which section that it's located the data in. Problems with scanning. Yara comes as a Windows 32 executable. There's also a distribution in Python called Yara-Python. The Windows executable offers the ability to scan with multiple threads, and if you're scanning the local machine, you can speed up the process greatly by spawning off 4 or 5 different threads. Unfortunately, if you're trying to scan over a network file share, you'll be limited to the throughput of a single thread. Also, if you're using the Yara-Python, you're going to be running into the global interpreter lock within Python. And basically, Python has a single global interpreter lock that manages its threads, and so the overhead of managing this and this single lock, you're going to actually find that it slows down the process by increasing your threads. It'll be faster to just scan with a single thread. The recommended solution for this is to use the Yara-C types. So let's talk about actually creating some signatures now. The first thing is to, as I mentioned ClamAV, you can create a hash of a file as a whole. You can use several different utilities such as MD5 deep, or you can use the Python with the standard libraries. The script that you see on the screen will do just exactly that. If you want to create hashes of the individual file sections, you'll need to use the PE file module, and the script that you see on the screen will do that for you. If you want to extract the individual sections of a file, The 7-zip utility will allow you to grab the individual sections so that you can do analysis on those. When you start writing rules, you may want an easy way to get started. And Yara Generator is a nice way to get started. You can create a free account on the website and upload your suspect file, and it'll create a signature for you. Just be aware that it will share the sample with other people. If you do not want the sample shared with others, you can actually download this to your local machine and then create your own signatures. And you see on the screen a sample signature that was created with Yara Generator. And you can see that it was nice enough to create a meta section and it identified the hashes of the individual files that were submitted. So what kind of rules could be useful? Well, we already have discussed that HR resume that came in that was detected by XOR rule. And it was basically looking for strings that are normally found and in fact must be found in an executable to run, and it just XOR encoded those values and it looked for those. This screen shows some rules that look for embedded executables, a Windows PE file, or DLLs. Where would this be useful? If you found an executable or DLL inside an image file, that is probably malicious, or perhaps within a PDF document. You don't necessarily care what type of malware it is, you just know that there's a presence of an executable, and that in itself is suspect. Perhaps you want to scan PDF documents. Yara supports the ability to separate your rules into logical sections to make them easier to maintain. For example, web pages use JavaScript, and so do PDF documents. Rather than maintaining your JavaScript rules in both locations, you can separate those out into a JavaScript rule and then include them wherever you need them. It helps encapsulate it so that it's a little bit easier to maintain. Now, the PDF rule that you see on your screen, I grabbed a lot of the actions from Didier Stevens' PDF ID tool, where he looked at the PDF standard and the various actions that automatically perform things within Acrobat. Malware authors will often send executables with the icon of an Adobe Acrobat document in the hopes of deceiving naive users into clicking on it. So you might want to create a rule based on some kind of resources or menus. And you can use Resource Hacker or PE View to extract the individual bytecodes that make up that icon. So if you see that icon combined with the executable, you probably need to investigate it a little bit closer. If you need a way to do easy string conversion from ASCII or Unicode to the hexadecimal characters, the script that you see on the screen will do that for you. But the best way to create signatures is to actually analyze the executable to understand what it does. And I like to use IDA Pro. And the reason I like to use IDA Pro is the flow graphs that will show the various code blocks, and that helps you understand the functionality of a program, and so you can look for specific things. For example, you could look at the sections that are responsible for creating network connections, perhaps the areas that are used for encoding or encrypting, or in the case that you see on your screen, the anti-forensics code. This code came from the Zeus Game Over Trojan and is part of what appears to be some anti-forensics code. But we need a way to translate these assembly instructions into something that we can create a rule with. Well, fortunately, it's fairly straightforward with IDA Pro. If you go to the Options menu and select General, then you can get the Disassembly tab. And on the right side in the middle is an entry that says the number of opcode bytes. The default is 0, which hides the instructions. But if you change that to something useful, like 6, then you'll actually see the individual opcodes that are used to create the instructions. You can highlight those and save them to a file for a rule. Now, one thing that you should be aware of is that system DLLs are often located in different areas depending on the version of the operating system or the language packs, so you may want to wildcard some of those addresses. So let's put this to the test. Probably the best way that we can actually create a payload and detect it is to use the Metasploit Community Edition within Kali Linux. And so I used the reverse TCP interpreter payload, and I sent it through MSF encode with the default encoder of Shikata Ganai and the default template, and I created 5 payloads. It would be nice if we could create some kind of commonality to discover how they match. Now, I'm not sure who discovered this, but the first time I encountered this was in an article by Mandiant, or blog posting, in January of this year. And they were discussing how that you could do common attribution based on a hash of the import table. What happens is a developer will get their toolset set up, and they'll often include certain libraries that they're used to using the function calls. The order that the libraries are loaded and the function calls within them will create a unique pattern whenever the file is compiled and linked. And that hash table will have a unique signature. So to test that, I grabbed the imp hash of some common utilities such as the MD5 deep utilities, and I found that the tools in that suite all had the same imp hash. Also, I tested it on the 7-zip utilities, and I found a couple of other files that shared a common imp hash. The script that you see on your screen will compute the imp hash using the PE file module to Python. And so when we test that on the 5 interpreter payloads, we can see that they all do have the same imp hash. But is that something you want to create a file signature for? Not necessarily. I mentioned that when I created the payloads, I used the default template. And the import hash table is actually part of the template file. So if I created a signature based solely on the import hash table, I would probably have a false positive. So when I actually look at the hashes of the individual sections, I discover that the 5 interpreter payloads each have 4 sections each. And of the 4 sections, 3 of the sections are identical. It's only the text segment that differs. That looks like that is a likely place for the payloads. Wonder if we can extract that out and see if there's any commonalities. And so I used the 7-zip utility to extract the individual sections, uploaded them to Yara Generator, and found that there was nothing in common. Yes, Shikata Ganai is very effective at obfuscating payloads. So we need to look at some other things to consider. There was a study back several years ago that looked at the entropy of files to determine if they had been packed or encrypted. Now when you're talking about entropy, most people are referring to the Shannon equation that begins with the number 0 and goes up to 8. The higher the number, the greater the information density. Back in the early days of computing, disk space was very expensive, and so developers needed a way to shrink their programs on the disk drive to cut down on the cost of using their program and be able to decompress itself in memory. And this was called packing. And there's a lot of legitimate programs that are packed even to this day. Malware authors discovered that packing had an interesting side effect, and that was to help avoid the casual analysis by people, so it could help them hide what they were actually up to. Malware authors were taking advantage of that, and so the more sophisticated developers of malware started actually using encryption. And according to this study, when they ran it across thousands of pieces of malware and a lot of ordinary files, they found that anytime the entropy value was greater than about 6.5, it was a good indication that something was either packed or encrypted. So let's put that to the test with our interpreter payloads. The script that you see on your screen will actually compute the entropy of the various file sections. And so you can see that when I run that on the 5 interpreter payloads, that yes indeed, the text segment has an entropy greater than 6.5. That's an indication that this is suspect. So let's kind of put this together. I mentioned earlier that Yara is available as a Python distribution. And we've talked about the PE file module within Python that lets us do some analysis. Well, wouldn't it be nice to be able to tie in ClamAV? Well, fortunately you can. Python supports something called C-types, and it allows you to bind to individual DLLs of other programs, and you can call the functions within those DLLs itself. And so the code snippet that you see on your screen actually combines to the libclamav DLL, and so you can embed your own antivirus program within your Python script. This could have a lot of interesting implications for you if you're dealing with branch locations or with other companies. So that if you had to ship it off to a remote location, you could send them a USB key, for example. Which brings up my friend Russell Butterini's incident response switchblade that he had discussed on Hack 5. He had a great little system that used a lot of open source utilities to gather information about a file to help locate malware. But one interesting dilemma is that if we're writing this in Python and the machine that's receiving this payload doesn't have Python, we still need a way to run. Well, there's a solution to that. It's called the cxfreeze module, and you can import that. And if you run it across your script, it'll actually create the DLLs that you need for distributing, and you can run a Python program on a machine that doesn't have Python installed. You probably want to include many of the sysinternals tools, such as AutoRuns-SC, ListDLLs, or SIGCheck, or any of the other ones to collect some of the data that you need for an investigation. Now, if you're trying to copy across the network using something like psexec, you'd want to create a single executable rather than trying to copy 400 or 500 files over. So there's several ways you can do that. There's the iExpress program that's included in your versions of Windows, but that's incompatible with the various versions. So if you're trying to use the iExpress that's bundled with Vista, for example, it will not work on Windows 8. You could use the 7-zip program to create a self-extracting executable. Unfortunately, when you run it, it's going to pop up a second window, which would hang up a psexec session. The best solution that I found is using something called inosetup, and it's a freeware software distribution mechanism. It will allow you to create a single executable that you can copy across the network using psexec, and then you can actually run the file within it. So in summary, your traditional antivirus programs are missing the newest threats, and you need a way to deal with these threats that are not being detected by your current signatures, because it can cause a lot of really bad things to happen in your organization. TrustWave in their 2014 global report revealed that 72% of all breached organizations are notified by a third party. Of the 28% that are able to self-detect, they dropped the mean time from detection to remediation down from a mean of 14 days down to a single day. So having the ability to detect this yourself and create your own signatures can help you avoid compromise. It can help detect it when it does occur and speed your remediation efforts. A lot of times management wants to buy expensive boxes with blinking lights, but sometimes the edge conditions will cause it to fail. And so understanding the process of how this works can come to your rescue. And as I mentioned earlier, many organizations cannot afford those expensive blinking lights. The QR code you see on your screen is not malicious, but it will allow you to get a copy of the slides. My contact information is on the screen. Thank you. Stop.